Welcome to this session of China. Today is the fifth Sunday of the month, and as promised earlier, we have from our labs directly for all our patrons, viewers. A fortnight back, Dr. Vijay Raghavan had given you a beautiful talk about the Nobel Prize related to same subject, and today we are here at the TI for Quantum Computing Lab, which is headed by none other than R.V. Let me tell you very frankly that this is one of the locations from where we telecast it. This is happening simultaneously from 3-4 different stations. So, and I wish all the team members the best luck. And there are too many of them for introduction. They'll introduce at the end of the thing. We're going to sit on a chair and then we'll introduce ourselves. Vijay, all yours and for your team. Thank you.
Thank you, Suren. Good morning, everyone, and welcome to this session of Chime Y, where we get an opportunity to actually look into the labs where all this exciting work is done. This is a new thing which has been going on for some time for the 5th Sundays. So it's a great opportunity for us to show you exactly what actually happens inside a lab and what it takes to do these experiments. We're going to be talking about quantum computing. That's one of the core areas of our work in this quantum measurement and control laboratory. As Suren said, my name is Vijay Raghavan. I'm an associate professor here in the Department of Condensed Matter Physics and Material Science. So we'll get started. I'll give you a very brief introduction to the idea of quantum computing. But what we will show you are the different steps that it takes to an experiment of this type. So we'll take you to the different labs where various members of my lab are stationed, and they will tell you about the different steps and the things you need to do in order to do an experiment in quantum computing. So let's get started. Madhvi, can we have the first slide up, please? So the essential idea of quantum computing is based on storing information in a very different way. So as I'm sure some of you know that in classical computers, which is the computers we use today on our phones, in our laptops and PC, there the information is stored in the form of bits. Basically, there are electronic systems inside your computers which can be in two different states, sort of like a switch. It can be either on or off. And it's just amazing that by having such a simple system and combining billions of such systems together, operating at speeds, in several gigahertz, that means billions of operations per second, one can actually make very powerful machines. The very fact that we're able to do this live without any professional cameramen and other things is a testament to the technology and how much it has advanced. And all of this is based on classical technology, right? The computing we are using. So what's the problem? The thing is that there are still some types of problems in science and in other areas which cannot be solved on today's computers, even though they are so powerful. Even the best supercomputer cannot solve them. And for that, we need a special kind of a computer. And these computers are what we're going to talk about today, quantum computers. So they have one very basic difference, that they use the idea of a qubit, which is a quantum bit. And the essential difference is that a qubit, instead of just being in this on and off state, or as we call 0 and 1, they also have the ability to be in what's called the superposition state, which is a combination of 0 and 1. Now, mathematically, when we write this down, we know exactly what we're doing. In plain language, all we can say is that it's a superposition state, or it's sort of both 0 and 1 at the same time. And it's this ability, when extended to many, many qubits, allows us new possibilities. Now, in order to make these qubits, you need different types of hardware, like a different way of storing this information. And that's what's now coming up on your screen. These are the different physical platforms for quantum computing. Now, of course, when we think about quantum mechanics, it's usually connected to the idea of atoms. We think that, in the quantum world is those of atoms. So some of the earliest approaches were actually using individual ions, which are actually suspended in electromagnetic field in vacuum, and you can address them with lasers. And that was one of the early ways of controlling them. In fact, in 2012, a Nobel Prize was given to Serge Haroche and Dave Wineland for developing these techniques. But since then, many other ways have been developed. For example, one can use an electron spin confined in a chip, which is often called a silicon qubit. And then moving on, we also have the ability to do this using light. Basically, you can use particles of light or photons to store this quantum state. And then there are other systems like nitrogen vacancy centers, and there are many, many more. We have only shown a few, but the one we're going to be telling you about today is a superconducting circuit. This is actually an electrical circuit which can show these quantum mechanical properties when you operate them under the right conditions. So as we go,
Shall I now reconnect from the instrument?
No, everybody should be back. All 8 are back. So you connect it.
yeah, what is the state of the YouTube stream? Yeah.
So just go to it.
Everyone was back. I guess.
YouTube will come. Yeah.
And then
YouTube is back.
YouTube is gone.
YouTube is gone.
You know, it's there. It's there. Yeah, it's there. Start. I think it's there. Okay. It's all good.
Next me.
Can't stop that. When did the audio goes? All right. Okay.
So you go back by 2 minutes or so.
Yeah, actually, can we go back to the previous slide? So, sorry about that, folks. There was a internet glitch here, unexpected glitch. Yeah. So I just quickly checked. I think this is where it stopped. So I was telling you about these different platforms with which you can build a qubit, and the one we're going to be focusing on is a superconducting circuit. These are electrical circuits when operated under the right conditions. Behave like atoms. In fact, sometimes we call them artificial atoms, and they allow us to do the same kind of experiments. The advantage here being that since these are electronic chips, we can potentially make them in large numbers, whereas at least on paper, it seems more challenging to be able to control that many atoms. But if you ask the experts in ion traps, they will tell you a different story. So anyway, I'm selling my platform here. But this is currently one of the most promising avenues for building a quantum computer, but so is ion trap. You must have heard about various companies called IonQ, which are developing it. And in superconducting qubits, of course, IBM and Google are the two big companies which are leading this effort. But this research is happening in lots of academic labs around the world, including ours. So what exactly is this superconducting qubit? I'll just give you a very quick introduction. It's basically, as I said, it's an oscillator. Some of you who have maybe studied electronics know about LC circuits and oscillators, but what we really need to think about is that any kind of oscillator. For example, a swing is an oscillator. Like once you set it swinging, it oscillates back and forth, and that's an oscillator. So what we do is we make electrical circuits, and you get some images shown here, which are taken using electron microscope, which also you will see later today. And these oscillators actually move at very, very high frequencies, something like 4 to 8 gigahertz. A gigahertz is 10 to the power 9 times per second. That is a billion times per second. So these are very, very high frequency oscillators, actually similar to the one which are there in modern 5G phones. But they have to be operated at very, very low temperatures. And you'll hear about that later. In fact, this machine you see behind me is the machine which allows you to go to very low temperatures. So these oscillators are essentially the qubits, and the states, the 0 and 1 states are basically when this oscillator is quiet. That means it's not oscillating at all. That we call as the 0 state. And then when it's oscillating with the minimum amount of energy allowed by quantum mechanics. So in quantum systems, the energies can be increased in sort of increments of a quanta. In fact, that's where the word quantum comes in. and that quanta is related to the frequency. So when the system is oscillating with the minimum energy, then we call that the one state, and then we can create states of the superposition by sending all kinds of signals to this device. So after we have one qubit, in order to make a quantum computer, it's very important that these qubits interact. In fact, that's how we do operations on a quantum computer. In conventional electronics, there is the idea of Boolean logic. You might have heard about NAND gates or OR gates, where two inputs come in and one output comes in. So the output is sort of the result of the calculation. Here, we have to do the same thing by getting these oscillators to interact. So you can now consider this as two oscillators. So I gave you an example of a swing, but a pendulum is basically the same as a swing. So you have now two pendulums, and these are oscillating individually. But if you want them to interact, you have to connect them together somehow. And when you connect them together, then they can exchange energy back and forth. And electrically, we can do that by just connecting these two LC oscillators, which are shown here, with this capacitor. And there are other ways of doing that as well. And that creates the interaction. And then in the end, you have to put many such objects together so that they form a network of qubits. And by doing operations on them, you can perform the different calculations you need for your quantum computer. Some of you might have noticed that the inductor is drawn in a funny way here. Parallel plate capacitor, of course, is symbol with two parallel lines. The other one is actually a Josephson junction. It's a superconducting device whose image you are seeing at the bottom. And it's actually what causes the system to behave like a pendulum. It's a nonlinear oscillator, but that's a technical detail. We will not go beyond that. So that's sort of the introduction, and as the essential ingredients is that we need to be able to make these qubits, and then we have to be able to make them in large numbers. And that's what we will show now from various labs, that how these qubits are designed, how they are made, then how they are measured, how to take them to low temperatures, and then finally how to control them. And then towards the end, we'll come back and talk about some of the details of the fridge, and also about how you take these experiments forward. So I'm glad you're all here, and so stay tuned, and we will continue, and we'll move to the next lab where we'll talk about the design of these qubits. So over to you, Bishop.
Thank you, Vijay. So here, basically, I'm going to show systematically how to build these qubits, how to measure these qubits. And so before doing anything building or fabrication, what we do is the simulation part. We need to know what we are going to build. So this is the screen you are seeing right now is a COMSOL multiphysics software. This allows us to simulate these things. You can simulate various things. Okay. Hi, welcome back. Sorry for the glitch again. So here, basically, I'm going to talk about one of the software that we use to do these simulations. So as Vijay talked about that, he showed you the slides of this, the system junctions and all. So before fabricating all these things, what we have to do is we need to know what we are making. So that's why we need simulation. And so this is one of the software that we use for these simulations. This is COMSOL multiphysics, if anyone wants to look. As name suggests, you can simulate different physics in this software. You can study airflow or compression, whatever you want. But we use a particular part of this, which is the electromagnetic wave, because we work in this RF regime where we sort of look at these electromagnetic waves. And so here, what I'm going to show is one of the crucial part of the measurement is readout resonator. So here, you can imagine you scooped out metal from a box. So what you have here is basically air, and surrounding we have a metal. So you can define a geometry like this. So at the end, sort of qubit will goes inside of this box. So once you have a particular geometry here, what you can do is you can mesh this geometry in the smaller parts. And what this software allows you to do is it solves the Maxwell equations on these smaller parts you can see. And it sort of combines all these equations and gives you the solution you're basically solving. So here what I'm finding is I'm using one of the sort of mode of the solving is eigenmode simulation. So I've already done this simulation. So I'm going to show the plots here. So now you can see this fancy plot on this. This is basically electric field, and color bar shows the field. The regions in the blue color are the sort of minimum field. Regions in the red color are the where the field is the maximum. Now you can see that at the edges it's the minimum, and then as you move to the center, it's a maximum. So you can just imagine this is same as when you have a basically guitar and you, let's say, strum a guitar. So how do you so what you get is the standing waves on the strings, and these are similar to the standing waves, but different boundary conditions, as electric field should be 0 at edges, and then you can see that these are the nodes and this is the antinode in the standing wave terms. So you can also get let's say higher mode of this. Let's say here you have two antinodes as antinodes at the edges, and node at the edges and antinode at the center. But if you go to the, let's say, little bit higher frequency, so it has this different kind of mode. Now you have two antinodes. So this is same as what happens on the string. So you have fundamental frequency, then there are multiples of that frequency. So now once we sort of do a complete simulation here, we know what the frequencies of these things are. And then once we know these things, so we design all these things in AutoCAD. And once we this designing part is finished, we give this to our workshop, which is like right across this lab. And then we get these cavities machined from the workshop. Can you zoom in? So this is basically whatever I was simulating is this empty part of these cavities. And now if I close this, I'll get the exact same thing which was I was simulating. So here now I've attached a coax port here, and you can basically measure what are the frequencies of this particular box using the VNA instrument we have right here, and you can verify the whatever you are getting in the simulation, are you getting that in actual measurement. So that's once this is confirmed, this is called a 3D architecture, where you have chips in 2D and this sort of box in 3D. You can do same thing in a 2D architecture. So in 2D architecture, instead of having these boxes, you actually have something like a string.
Sir, you need to share screen again.
Yeah. Am I visible, right? So here it's the same logic, but now you have everything in 2D. You can see that this is the sort of transmission line, and you can imagine this as a string. And this is sort of the mode that we use for the readout. You can see that at the edges, electric field is maximum. Then as you travel along this, it gets lesser and lesser. Then you have a node here, and then you again travel along. You have a maximum electric field. So you send in the excitation from this side. My qubit, the actual chip, will be sitting somewhere here, and that's how it gets excited via this particular resonator. And so this is called a 2D architecture. And so in 2D architecture, we don't have this kind of boxes. We have this kind of sample mounts where the signal comes in from here, then it goes to this RFPCB boards, and chip will sort of go here. So this RFPCB boards we also make in-house using this laser printing machine. This is sort of like a fancy milling machine. Beyond, yeah. So we're going to show that how we mill these things. You can start. So what we have is, you can kind of focus on this. You can see that this is the laser head which sort of milling out the unwanted part from the PCB. We have already board on this thing. So this is basically a particular dielectric board which has copper at the bottom and the copper at the top. It sort of looks like this, and you basically mill out the unwanted part from the top, and then one more turn, right? Yeah. You can stop in between. You can stop otherwise. Okay, take it. Is it correct? So here we need to know that how much we are milling and all. So that's why you have a calibration there. That's what this tool was doing right now. So we have a wedge, and at different position, it will have a different height. And that's how we know if you're completely drilling through the board or just milling the top part of it. Here we are just showing a simple example so that it will get over in time. I think it's almost done. Done. Yeah. Now let's see what it has done. You can see that this is what it has milled. From here, it has removed the unwanted part, and this is sort of the design we fed to the this particular machine. So here also we design these things in CAD and then feed to the machine, and it sort of prints as we want. So you can basically different kinds of PCBs. Sort of the one I was showing here. I have a PCB which like this is what sort of we make, and we showed a simpler version. So this one is also made here, and once we have this, we sort of glue it on the top of this, and once we glue this, and then we sort of stick our sample here in this 2D architecture. In 3D architecture, we sort of place our sample inside this thing, and we enclose this. And to make a sample, we need to go to clean room, and Srijita in clean room is gonna basically talk about how we make these samples. Over to you, Madhvi.
So now that we have the designs planned out, we have the box cavities and all the 2D PCBs ready. We can now go over to the So the process that we use for making the patterns on chips is a process called lithography. Lithography is basically the idea of making an in situ stencil on top of the substrate where we want the pattern to be. And that process of making the stencil is done by putting a layer of a polymer, which when exposed to a certain pattern of either UV light or electron beams, that solubility of that polymer changes. And then once the soluble polymer is removed, we have a sort of stencil that is prepared on top of the sample itself. So I'll just run you through a very quick little animation for this. So we start with a substrate. We put on this polymer resist that is sort of very carefully calibrated chemical. We then expose it and generate the pattern. So this exposure will be either light photolithography or electron beams. Then wash off the soluble part. Then we are now ready to deposit metal on top of this sample. And once the metal is put by various metal deposition techniques, we'll be showing you our evaporator where we normally work. And then we remove the resist. We have the pattern prepared on top of the sample. So here's just an example of one of the kind of patterns that we can make. Now, this idea of lithography is essentially what is used in the entire chip industry as well, because whether it's Intel or any of the others, the chips that are inside your phones and cameras and laptops are all made using this essentially the same process. The same process can also be done by starting with a metal. So it depends on what design you want to make and specifics of what you're making. You can start with a metal, do a patterning, and then do a process to remove the metal wherever you don't want it. So with that little introduction, let me take you over to the clean room. And at the clean room, we have Anirban and Srijita. They're going to show us around there. But before we actually go there, I'm going to just introduce the idea of the clean room. So why do we need a clean room in the first place? Now, the patterns that I showed you on the chips are actually, very, very small scale. Some of them are on the scale of microns. Some of them are even tens or hundreds of nanometers. And on that small scale, if you were to have any dust particles, fibers, anything like that, that sits anytime during the process of fabrication, then that would basically ruin your sample completely, your device completely. So for this, we work for these kind of processes. We always work inside a clean room, which has an active filtration system to filter out and remove all particulate matter as far as possible. So in typical ambient air, particulate matter is like of a certain size. You will have 35 million particles within a cubic meter. But in the clean room, there are different grades of clean room where you can restrict that particle matter to say to 100 particles or 1,000 particles or 10,000 particles, depending on how how well your clean room is designed. So these are now views of our clean room. Unfortunately, we've had a routine power shutdown here recently, so we are unable to at the moment turn on any devices inside the clean room. We'll not be turning on anything. We'll just explain it and show you all the equipment, and we'll supplement with some videos that we've taken previously to show how certain things are working. So, so in a clean room, there are, now thanks to COVID, we all know about HEPA filters. So there are all different kinds of filters, including HEPA filters, to filter out the particulate matter. There are some filters there, that are being shown up there on the ceiling of the clean room. And also the clean room, you may notice, is all yellow light. And the reason for this is because in photolithography, ultraviolet light is what is used to expose the resist. So we do not want ultraviolet components in the ambient light over there. Okay. So, and also, Srijita, if you can just show Anirban, we also all wear these clean room suits because we don't want, any body fibers or any dead skin kind of stuff coming on any of the work that we do. Okay. So the first step is the spinning of the resist on the sample, and Anirban is going to show you the fume hood where the spinning takes place.
Yeah, so guys, this is actually the fume hood in which the spin coater is there.
Anirban, can you speak a little louder?
Yeah. So this is actually the spin coater that is that we are going to show you a demo how we do the spin coating. And this is actually the chemical hood where the spin coater is inside. We are using a chemical hood because we want to evacuate any harmful fumes which may be present in our chemical resist. So since the Madhvi has already told you that we are actually going through a power shutdown, I cannot show you live how we do the spin coating, but we will show you in a video. So Madhvi, can you show the spin coater, and here is a resist which will put some drops onto the chip, and we will start the spin coating. So basically the chuck will rotate at a particular speed, which depends on the how much thick you want to put the resist. At a particular amount of time, the chuck will rotate. And when you have like a uniform layer of resist on top of your chip, you will need to bake the chip at a particular temperature to harden it. Like in the video, you can see it's baking at 180 degrees Celsius for roughly like 1 minute or 2 minutes. And now you have your chip ready on which you have the resist layer. Yeah, so once you have the resist layer on top of your chip, now you need to pattern your mask on top of your resist layer. And for patterning, we use electron beam lithography, as already told by Madhvi. For doing that, we use this machine, which we call as the nano fabrication tool from Lathe. So here, basically, it also acts like a scanning electron microscope, but we are using this tool to do the lithography. So since I cannot show you what is inside this equipment, I will briefly give an overview. So on top, you have this gun, which acts like basically a source for basically shooting the electron beams on inside your chamber. And you have this sample holder on which we place our chip, and we insert this sample chamber through this gate inside this chamber. And when the gun shoots your electron beam, it actually goes through a particular system of electromagnetic lenses to focus your beam precisely onto your sample. And then you have this kind of beam deflectors, which actually deflects very fast onto your sample depending on the pattern that you have. And since we do not use a physical mask here, we are actually using a CAD design or computer aided design, which acts like a mask, and that is being fed inside this equipment through our PCs that you can now it's turned off, but we can do that through these PCs, and that actually allows us to program and design our pattern onto the sample. And yeah, so here Madhvi, okay, so Madhvi can just go back and yeah, so here, as you can see, it's we had taken a photo of the inside of the chamber. So on the top, it's basically showing the one part of your column in which on the top is your gun monitor, and then you have the lenses, and then you have the beam deflectors. And you can also see this sample folder, which is now in the photo. You can see it's inside the this equipment. And so now just Madhvi, just go to the CAD design. Yeah, so here this is one of the files, the computer aided design files that we use to make our design. So the gray regions or the blue regions are those in which we want to expose our beam, which we call as the exposure, because those are the regions where the beam will be coming down and the that will be focused onto, and this is what we call as exposure. And now, so after this, so basically this pattern will be designed on top of your resist. Yeah, so this is how the chip will look like after you have taken out the sample from your Lathe equipment. And then when you have the then you have the resist profile on top of your sample. What you have to do is we use a chemical called a developer, which basically submerges your resist which have been exposed from the e-beam. So now in this picture, you can see the black regions are basically now the resist profile, and the pads that you see here are basically the substrate. And one thing to be noted that this whole thing is going, the vacuum is going inside a vacuum. So the pressure maintained has to be like around 10 to the power minus 9 to 10 to the power minus 10 millibar. Okay, and also for better resolution of our beam onto our sample. So using these PCs, we can actually manually adjust the focus and also correct the stigmation so that we get better resolution. And one advantage of this electron beam lithography is that you can actually get very narrow resolutions, like up to like 10 nanometers scale. And depending on your pattern, it may be just these two boxes, or it can be complicated designs. This will take some amount of time. So yeah. So now I will also like briefly take you to that chemical hood where we use this all chemicals that we have. Like we use the developers to like develop the resist, so that we now have a proper pattern of the resist profile onto the sample chip. And this is all that I want to show you for now in the clean room. And now we will also show you how we deposit our metal on top of the resist profile. And maybe Kishore will talk about that. So over to you, Kishore.
Yes, so I'll come in for a second. So once the stencil is prepared on the sample, then the sample goes into our evaporator. And so we'll go back to Kishore, who's in the evaporator room, and he will just show us the evaporator now. Over to you, Kishore.
Hi, welcome back. So now Anirban has showed you how we make these chips. So once we have these chips, so what we do is we load it inside the evaporator. So this is the evaporator made by an Indian company, and this is Excel instrument formed by a ex-TFR member only. So we have made this as per our requirements. So as you see here, we have a sample chamber. Sample sort of sits on that sample head. And then we have this main chamber where all the metals and all parts are there. Then we have on top of there is a buffer volume which used where we store our oxygen for oxidation in between. And this is sort of a control rack for this. As you can see that the pressure in the main chamber is to 2.1 it is about minus 8 millibar. That's like a very low pressure. And so that's why you need something which is like a load lock or a sample chamber to load your sample. So what we do is we load our sample here. So till this point, these two chambers are isolated. And then once we load the sample, we pump it till a reasonably low vacuum. And once it's pumped to that particular vacuum, then we open this gate wall. And then sort of we like pump it for a minimum 12 hours. So that's for the vacuum requirement. And so why we do it? So here what we are using is e-beam evaporation. So we are actually will be using e-beam to evaporate this metal. So mainly we do aluminum here. And so if you have a ultra low vacuum, then this evaporation will be highly directional. And that's what is the main advantage of this particular e-beam evaporation. So once we have this highly directional evaporation, so what we do is a double angle evaporation. So this is the control we have for controlling at what angle we want to evaporate. So we basically rotate the sample head. So, and then that's what fix the angle. So then we basically evaporate at some, like, let's say, for example, plus 20 degrees. And then we also then we do oxidation in between. And then we evaporate at minus 20 degrees. So this basically two evaporations separated by this oxidation sort of forms a Josephson junction. This is called the Dolan bridge technique, and you can read about it in details to actually know what it is. It's quite simple. And so this is basically deposits thin films of the aluminum into different evaporations, and thicknesses of these thin films are first evaporation we do at 20 nanometer, and the second one is at the 50 nanometer. So these are all calibrated numbers, and you can measure these thicknesses by, so we have a sensor inside this, which is a, I don't know whether you can see. So yeah, we have a sensor head inside this, which sort of measures how much, yeah. So which measures how much material is getting deposited on that sensor. And so we know that if metal is getting deposited on the sensor, it will get heavier and heavier because it's adding on the mass, and that changes the frequency of the sensor. And that's how we know how much thickness is being deposited. And once all this evaporation is done, we do a lift-off in the chemical hood, and this lift-off process basically removes the unwanted metal. And once we have removed all this unwanted metal, all we are left with this kind of chips, where you can, I don't know if you are able to see, this is like an entire chip that was loaded in the evaporator. Now you can see some shiny patterns here. So these are basically multiple copies of what Anirban showed you the CAD design of. So these are the multiple copies, and we can't basically load all. So we do some room temperature resistance measurements, and we decide which qubits are the good qubits. And from this chip, so I have already pre-diced chip. So we sort of dice that big chips into the smaller chips. And now each one of this is a qubit. And so this qubit sort of will be placed inside this cavity, which I showed you earlier. Now you can see that I have placed the chip here. And once this chip is placed, I close this cavity very nicely, tight these screws. This is very important. And this is for 2D architecture for 3D architecture, I'm sorry. And for 2D architecture, I have a similar chip, which Madhvi showed earlier in your presentation. You can see that this is a 6-qubit chip. So this chip sort of will go on top of this 2D mount, which I have here. It sort of goes like this. We sort of glue it using, and then sort of it goes like this. Now the signal can come from here. It goes to RF PCB board, and then from the RF PCB board, we sort of use wire bond to launch the signal onto the chip. And once you have this ready, so this will be mounted inside the fridge, and this fridge goes to like 10 to 30 millikelvins. So to get to know about what's actually happening inside the fridge, what are the wirings inside the fridge, we go to Vijay, who is in CG, and he'll talk about this in more.
Unmuted. Okay. All right. Welcome back. So now I wanted to show you the insides of the dilution switch, where all the wiring is and how we actually wire it up to do the experiment. So we just saw how the chips are made and how they are put inside sample box. Then they have to be put inside the dilution refrigerator, which is shown here. What you're seeing here is a partially open refrigerator. This plate here, this big circular plate here, is the part which gets down to the lowest temperature. And this temperature is 10 millikelvin or 0.01 Kelvin above absolute zero. So it's very, very low temperatures. And you need such low temperatures because temperature is sort of it's a kind of energy. You can think of temperature as a measure of energy. And the oscillators I talked about, ones which either are quiet or oscillating with the minimum amount of energy, that minimum amount of energy is so small that if we operate these things at room temperature, the thermal energy is so high that you will just not be able to do anything. It will completely destroy them. It's like a noise. So in order to suppress that noise, we have to go to very, very low temperature. So Gaurav, if you come over here, the active part of this refrigerator is actually here. This little thing at the bottom I'm pointing is called the mixing chamber. And inside this, there is a combination of helium-3 and helium-4, which are two isotopes. And it's the physics of the phase separation. It means like they actually float like oil on water, which gives rise to this cooling. So I don't have time to go into the details of the cooling mechanism, but it's just a more sophisticated version of what we call evaporative cooling, which is what happens when you put water in a pot and the water seeps out and it evaporates and it takes some energy away. So here the evaporation is actually forced with the help of pumps, which are connected to this system. And ultimately, this part gets down to about 10 millikelvin, and whatever is connected. So this entire metal plate, and this metal plate is basically high quality copper plated with gold. That is just to prevent corrosions, because everything has to be in contact. So whatever we attach to this plate gets to that temperature. So now you are seeing all these different wirings here, and this is how the signals are brought in. So Gaurav, if you go here, you can see there's a whole bunch of wires coming down. In this refrigerator, there are 24 wires total, and some of them bring signals into the system and some take signals out of the system. And they have to be made using special materials, because when you connect two different plates like this, which are at a different temperature, you have to be able to maintain that temperature difference. Just like in a flask, you have the inside the liquid is hot, but outside it's not hot. So you have to make sure, otherwise you will never be able to cool down. So special materials are used for making these cables. And then these cables are essentially a sophisticated version of the kind of the cable antenna cable you have. They're called coaxial cables, and they allow you to bring us these high frequency signals I talked about, 4 to 8 gigahertz, all the way down from room temperature. So if we stand back here, the signals are actually being generated from this instrument rack, where there are lots of the signal generating systems here, and they are all going through these blue cables all the way up down here. And then at the top, which you can't see right now, there are ports where they get connected, and then they come all the way down from room temperature down to 10 millikelvin. And a care has to be taken that this is done properly. Otherwise, this wiring itself would load the system and prevent the system from cooling down. So down here, the actual experiment is inside this cylindrical box, which we have not opened, but the experiments, the ones Kushore showed you, like the cavity, are mounted inside, and it's covered inside a shield, because we actually have to protect that device from all kinds of noise. Now, one of the strange things here is that even some of the hotter parts of this fridge, even though these are very, very cold, for example, this one is at 10 millikelvin, this one is at about 150 millikelvin, but there are other plates here which are at higher temperature. They actually radiate heat. It might seem very strange because this is very cold, but it's all relative. A higher temperature system will radiate heat to a lower temperature system, and that can actually affect your experiments. So we have to put inside a shield. There is actually another shield as well, and several layers. So we have to do it in multiple steps, and only then we can protect the system and reduce the noise to a level that we can see that tiny excitation of the qubits which we're trying to do. We also need lots of specialized filters, which are shown here, and some of them are commercial, some of them are homemade, and we need to combine them. So the wiring in here will allow you to, control maybe about 8 qubits or so. And some of you might have seen images from Google or IBM, and you see that they will have many more wires to control many more qubits. So this is actually one of the challenges, that as we try to make a system with larger and larger number of qubits, you're going to need much more wiring. So people are also building fridges which are much bigger in size, and that's how this technology is going to scale. Some people say that this is one of the roadblocks, but currently it's not fundamentally a real problem. It's technologically challenging, but it can actually be done. So once you put the devices in, do all the wiring, and then do all the filtering correctly, then the system has to be closed, because we cannot cool it like this in ambient condition. And that's what you're seeing here. You can see all these different shields. This is the outermost shield, which allows us to create a vacuum inside, because again, you don't want any of the air to freeze on these surfaces. And then you see there are these various different metallic shields, 1, 2, 3. These are called radiation shields. They are actually protecting the very cold part from the very hot radiation from this side. And that happens, all of these are at different temperatures. So this radiation from this is absorbed by this little shield here, which is at about 50 Kelvin. And this 50 Kelvin radiation is absorbed by another shield at 4 Kelvin, and 4 Kelvin radiation is absorbed by another shield at about 1 Kelvin. And these higher temperature stages can absorb more heat, but the lowest temperature ones cannot. Right? In fact, the lowest temperature is decided by the balance of how much heat we are removing versus how much heat is coming back in. So we have to close this up. So we move on to the video, which actually shows this process very quickly, what happens when you actually close the system up. So Madhavi, can we play the video? Back to the other lab where we have a video of the fridge. So you can again see a similar looking shield inside with the thing. And now they're bringing the first shield. This is what's called the still shield. And they are using gloves to make sure that they don't get their greasy hands on the things, because that affects the conducting properties of these shields. So Srijita and Jay are
closing this up. So there are various screws which have to be tightened in a specific order and very carefully so that the thing connects to the top layer properly. And then you have to bring each one of these shields one by one. So earlier in the live thing, you saw the one half of the shields. Now here you're seeing the second half. Of course, it's a different refrigerator, but finally you have to put all of them, and then the vacuum can comes next. It's much heavier, so we have to use a hydraulic lift to slowly bring it up. And then once that gets loaded and we tighten it, then we connect a pump to the system, a vacuum pump, which removes all the air and creates vacuum. And then basically the fridge's control systems take over, and then they cool down the system. It actually takes about 24 to 36 hours, depending on the type of fridge, to go all the way from room temperature down to the base temperature of about 10 millikelvin. Finally, this last thing is also a magnetic shield, which protects the system from magnetic noise. So that's about the fridge closing. We now go back and to W105 lab. So over to you to look at some live experiments.
Hello everyone. Today I'm going to show you a couple of single-qubit experiments that we are doing.
Gaurav, I can't hear you properly.
Hello?
Not really.
Am I audible now?
Yes, you are.
Yeah. Hello everyone. Today I'm going to show you a couple of single qubit experiments. Right now in the fridge, we have cooled down a fluxonium qubit, which is a novel superconducting qubit. On the screen, you can see a CAD file, which we given before, making the stencil that Madhuri talked about. What you are seeing is in this diagram is that the extended green pads, the extended lines, is basically the antenna for the qubit to communicate with the cavity, which is being cooled here. And at the center, there is a bunch of Josephson junctions, a structure of a bunch of Josephson junctions. Yeah, this is what the zoomed in image looks like at the center. And after the fabrication, the final device looks like this, where there's this array of Josephson junctions, and there's a small junction which is not visible here. This is an optical image, but there's a small junction here, and this makes the fluxonium qubit. The very first experiment that I'm going to show is the Rabi oscillation experiment. It's basically a control experiment. You want to characterize your control, and this is the starting step. So I'll start the experiment. What I'm doing here is basically I'm giving it a microwave pulse at the qubit frequency with a varied length. What if you coherently do this? If you coherently put in the pulse onto the device, the state of the qubit starts to rotate. It will rotate between the state 0 and 1, and that is what the oscillations here have been shown. These are the Rabi oscillations. The next thing we do is we fit this Rabi oscillation to calibrate the exact control of the pi pulse. I mean, the pi pulse, what pi pulse does is it takes the qubit from state 0 to state 1, from one pole to the other. You can what you are actually seeing is actually I've run a 1 microsecond microwave pulse till microwave with the varied step size, and in the varied step size you can see that the qubit is oscillating. It's starting from ground state, which roughly here is represented by this arbitrary unit 2, and it's ending up in the excited state, which is arbitrary unit -1. Now after that we fit the data to calibrate the pi pulse. You can see it's approximately 74 nanoseconds, and this is how you calibrate the pi pulse. The next thing we want to calibrate is actually characterizes the relaxation time of the qubit. Now the qubit actually spontaneously decays if you prepare it in the excited state. All right, prepare in excited state. So for this experiment, what we do is once we have calibrated this pi pulse, now you know that you can control your qubit and send it to excited state, state 1. After some time, after After once you put in this pi pulse, you wait for a little amount of time, and then you read out the qubit. And from that, you can see that it starts at an excited state, but spontaneously it decays to ground state. I've loaded the experiment. It will take like a couple of minutes, 1.5 minutes to be exact, for the experiment to be loaded. Once we have done all of the characterization of a single qubit, the next important step is to perform 2-qubit experiments and to exactly control 2-qubit operations, 2-qubit operations. Once these are done, then you can think about scaling up the qubits. Just a moment. The experiment is going to be loaded. No, yeah. At this moment, we are actually 2-qubit cooldown has been cooled in the fridge. We are the 2-qubit experiments are ongoing. Yeah. Now you can see over in the experiment that the qubit has been at the starting of the graph. The qubit has been prepared in the excited state, and it slowly is decaying into the ground state. And we fit an exponential decay to this plot, and we can extract the T1 number. This is basically the relaxation number we use as a metric to characterize our qubit, and you can see it's about 20 microseconds right now. And then this number actually represents the fact that it's a metric that that you can show that the qubit is decaying and how long the information is lived. Thank you. Over to you, Madhu.
Thanks, Gaurav. So now that we've spoken, Gaurav has spoken about measuring, and understanding single qubits, and a little bit about how we need to then couple these qubits together to be able to perform gates and to perform any kind of operations. We now come back to Vijay, and he's going to talk a little bit about the scaling up and how we need to actually build this up to many more qubits and the challenges that lie ahead.
Okay, welcome back. So you just saw this qubit data being taken live. And what you noticed, some of you might have been surprised that the time scale over which decays is actually quite short. It's about 20 microseconds. And that's actually one of the main challenges for building a quantum computer. Almost all kinds of qubits are unstable, but they have stability of different ranges. Superconducting qubits typically have about 50 to 100 microseconds time scale. And though things have been improving, just to give you a sense that in 1999, when the first superconducting qubit was made, the coherence time, or basically the time scale over which decayed, was about a few nanoseconds. And now we're already at about 100 microseconds or so. And there have been experiments where people have approached almost a millisecond. This is important because when you're doing your computation, you don't want the system to decay, because then the computation is essentially garbage. So right now, the state we are in is that the experiments have to be done in a very, very short amount of time compared to the time over which these systems decay. So that's typically what we call the decoherence time. And what is really important is how quickly you can do the operation. So you saw this pi pulse calibration. He talked about 70 nanoseconds. That's actually slow. You can make it and make it faster to about 5 or 10 nanoseconds. And then that's sort of a measure of how long it takes to do one operation. A 2-qubit gate might take about 100 nanoseconds or so. And then you can see how many such 100 nanosecond operations you can fit over this time scale of about 20 microseconds or so. But actually, not even 20 microseconds, because by 20 microseconds, there will definitely would have been many, many decay events. You want to do it in much, much shorter time. So these are often called, they have been given this name that we are in this noisy intermediate scale quantum error. Noisy here refers to the fact that these systems decay, and that gives you inaccurate results if you do a long computation. So one of the challenges is related to this aspect of decoherence. And a simple way of understanding the decoherence is basically to say that, these systems decay, but in the oscillator example, when you take a pendulum and you set it to oscillate, at some point it stops oscillating. That's essentially decoherence. In the case of just a regular pendulum, it's friction which is causing the system to decay. In the case of superconducting qubits or other things, there are other kinds of mechanisms equivalent to a friction. Okay, so this is one challenge we have to work on, and people have been improving. As I said, we have come from a few nanoseconds all the way up to hundreds of microseconds, and further progress is being made. Eventually, once the errors are low enough, it's actually possible to combine many qubits which are individually bad, but together they can actually be good, and that's called an idea is called quantum error correction, and this is going to be a very, very crucial and important step to do that. And for that, you have to combine many qubits. Now, what is the other challenge? I already mentioned that we have to do a lot of wiring, but that's something technical, can be in principle will be solved. But we also have to create different kinds of architectures to put these qubits together. Now, typically, qubits when they are laid out on a planar interaction, not every qubit is interacting with every other qubit. And that is actually also places a limitation, because it actually makes the execution of an algorithm, that is the problem you're trying to solve, more complicated. It adds more steps, and more steps means more chances of error. So one of the things we are trying in our group is to come up with a new architecture. So Gaurav, maybe if you can zoom in, and this is called a ring resonator based architecture. And what you are seeing here is a mechanism where there's a circular path here. So I don't know if you can see that very clearly. So the lighting, yeah, maybe this is better. Yeah. So you can see there's this little circle in the middle, and then there are these little things sticking out on all sides. So these are the locations where actually the qubit chips will go, right in one of these gaps between the spokes and the circular thing. And this is an architecture we are developing here. So in this particular system, we can put 12 qubits, but we have designed in such a way the circular path actually connects most of the qubits to most other qubits. So in this architecture, we showed that it's possible in principle to connect each qubit to 9 other qubits. There are a total of 12 qubits. So 2 qubits don't interact with each other. That comes because of the physics of interference of waves. We won't go into the detail there, but this is an important activity which again many other groups are also doing, to try to figure out ways to connect many qubits to each other, and because that will make the processor more efficient. One of the other things we are working on, and as are several other people, so if you go to the instrument rack here, you saw this whole range of equipment which is used to control. So approximately, again here, the amount of equipment here is only enough to control about 4 qubits. These include the systems which generate the pulses. So these are all commercial instruments we have purchased right now. And then there's a bunch of microwave control electronics here at the top. But as we go to hundreds and thousands of qubits, we're going to need much, much more. So this system is going to become very, very large and unmanageable. So one possibility is to use some modern technology like these green colored boards here. This is a technology which has actually emerged because of the 5G revolution, because remember I told you the same frequencies are used in these 5G phones. So they have found out a way to generate these signals in a compact and efficient way. So this one board will actually allow us to control about 16 qubits, as opposed to that entire rack of equipment you just saw, where that is just enough for about 4 qubits. So eventually these kind of technologies will be developed, and we have to miniaturize the electronics and make it more cheaper and scalable. Also, the cost of this is about 10 times smaller than what you saw in the instrument rack. So we also have projects here where we are working with scientists from various other institutions like DRDO to develop this electronics, and also with BARC and other places. So that's sort of where things have to go. We need to make better qubits. We need to find ways to create a network of qubits where the interactions can be a lot more dense, so that you can reduce the number of operations. We have to develop quantum error correction so that unstable qubits can actually still be used. We will never be able to make a perfectly stable qubit like a classical bit. When we store information on your hard drive, it can survive for years. And here we are talking about tens of microseconds. That's when the information can survive. But once error correction is built in, we will be able to use this in an efficient way. And that's a major, major milestone. And then then from the technical point of view, we have to figure out how to build large refrigerators and more compact electronics. But this is, of course, very specific to superconducting technology. But for all other qubit platforms, say ion trap, there are similar challenges but at different levels of complexity. So that's sort of one of the reasons why we don't know exactly which technology is going to win in building the first practical quantum computer. We have prototypes available in ion traps and superconducting qubits right now, as I'm sure you're aware. So that's sort of the story. I hope you got a sense of what it takes. The idea here was not to really explain the science in a lot of detail, but to give you a flavor of what it takes to do research of this type. So you see there are many, many steps, starting from designing the qubit, simulating the design, then going and making the devices, mounting the devices, ensuring all the shielding is done properly, using cryogenic systems to cool the system, and then finally understanding all the microwave electronics and control. So it's really a job or a task which requires lots of different kinds of skills. And it can be a lot of fun. That's why we have a large team. You got to meet many of them, and you'll now see all of them in the question answer session. So just pause for 1 second while we position ourselves, and then we will take questions from YouTube. If you have not already asked your questions, please type them. We will go through them and try and answer as much as possible. Thank you very much.
Thanks, Vijay. Ulhas, could you just turn on the camera?
This central location, you should appreciate the number of people involved, and it's like just like a great team of cricket. You have bowlers, your wicket keepers, your batsmen. Everybody has their own role to play, and at the same time, you also have all-rounders like Kapil Dev, Nikhil, and other people. So we have our captain coming in a few minutes, and the other people also coming from various stations. So this is nothing but like a cricket team, and everybody is an expert in their own field, but they also overlap on various other things. Thank you, Vijay, and the entire team for such a nice show. I'm waiting Vijay to come back. Yeah, it's coming now. Okay, fine. So in the meantime, there are a couple of questions which have been posed, and the kind of technology that is going into experiments of such kind and the complexities. There are lots of questions, but there is no silly question. Let me put it very frankly. There is no silly question, because whatever comes to your mind needs to be answered in a very appropriate way. So very first question is, when the aluminum superfoods at some, becomes superconducting at little over the absolute zero, why do you need to go down to such, millikelvin range? That is the most important thing that has come to the fore. Does anybody in your team would like to answer? Oh, the captain is here.
Hello, everyone.
So one person is missing right now, but otherwise 10 people are here.
Maybe before we answer the question,
Let's introduce.
Let me start here. This is Lakshay. He's one of the younger students in the lab. Then we have Gaurav, who's actually from the Center for Excellence in Basic Sciences in Mumbai. He's doing his master's thesis here. Anirban is a senior PhD student whom you met in the clean room in the gown. He is the one, now you see the real person inside. Shrujita is also a fourth year student, fifth year student, and she's also the person in the clean room. I'm Vijay. I'm the associate professor and the principal investigator of this lab. Suren, you all know. Madhavi is a postdoctoral researcher in the lab and has been associated with us for many years now, and she's sort of a resident fab expert. Gaurav, you saw explaining the data of the live taking. He's working on these fluxonium qubits, which is a different type of a qubit than the one we mentioned in the beginning. Kishore is also a senior grad student. He's working on a new type of qubit design in our lab, and he was the one who showed you the COMSOL simulations and the other aspects about evaporation and putting together the chip. And then we have Ishita and Panya. They are brand new students. They are just entered the lab and they are learning the ropes, and they have helped out today for this activity. So let's get started. Who wants to answer the 1 Kelvin question? Should we actually quiz some of the younger students? Panya, you want to answer this question?
So, as someone correctly pointed out, that aluminum is actually doesn't have a TC which is as low as millikelvins, but we still need to go down to millikelvins because of thermal noise. Basically, the spacing between the energy levels, as Sir pointed out, that qubits are nothing but harmonic oscillators. The spacing or the energy spacing between the ground state and the first excited state is of the orders of, say, so the h omega naught there has to be.
What does H omega mean? Most of us do not understand what H omega
Can you
is.
say the energy scale?
So the energy scale there is the temperature equivalent of that is such that we need to go to millikelvins, so that no thermal noise is exciting those energy, basically going from ground state to excited state, and we are actually measuring the real real experiment which is taking from 0 to ground and vice versa.
So I can add some more technical points. So as Panya correctly said, it's really about making sure that the thermal energy is much smaller than the energy separation between our two states, so that we don't create any random states. But there's actually another aspect to it, which is connected to decoders. Now, superconductivity is actually not like a on and off switch, that if we say the aluminum has a TC of 1 Kelvin, which is basically what we call the transition temperature, that it becomes perfectly superconducting immediately after you cross the temperature. Actually, there is a certain number of, so the electrons, we call them, these electrons condense into Cooper pairs, and those are the ones which superconduct, but some of the regular electrons still survive. And as you go to lower and lower temperatures, the number of those regular electrons, and these regular electrons are the one which give you dissipation or friction. And in order to suppress those also, we have to go to much lower temperatures. Probably not 10 millikelvin. That probably will maybe taper off maybe around 50 millikelvin or so, that the suppression is enough to not worry. And you don't want this friction to be present for this oscillator. So that's the second reason why you want to go to much lower temperatures.
So Vijay, there was another question about why do you need to go to the low temperatures at 0.1 Kelvin? So you have mostly covered that, but then there's another question which is coming up, and that question is you must be requiring a lot of shields for the room temperature to be segregated from the sample. So what are the shields and what's the material which is used for such shields?
So I mentioned this earlier while we looked at the closing of the fridge. The shields are made out of regular metals. You just have to be good conducting metals. So they are made out of two different metals in this case. One is aluminum. So the light, silvery things you saw, those are aluminum, and the brownish ones are copper. And in fact, if you maybe pan over here, this is one of the shields you just get upside. So this is an aluminum shield, but there's actually a nice shining mylar film, which is aluminized like film of plastic. This actually is a nicer, shinier thing, and that reflects the heat better. So this is basically a way to reduce cost, because otherwise you would have used copper, which is the one we use for the lowest temperature. But for the higher temperatures at 50 Kelvin and 4 Kelvin, they lower the cost by using aluminum, but then still improve the ability to shield by putting this mylar film. So the 4 Kelvin shield has the mylar film, and then the 50 Kelvin shield doesn't have the mylar film. The main reason is that these are connected to certain parts of the refrigerator which have a larger ability to absorb heat. So at 50 Kelvin, you can absorb a lot more heat, but at 10 millikelvin, you cannot absorb any heat, because any heat will raise the temperature. So we have to have these multiple shields in order to suppress all the radiation, all the way from 300 Kelvin down to 4 Kelvin stage. So that, and then the radiation is low enough. In fact, there is an added crazy thing which is not related to the temperature aspect. The fact that this 4 Kelvin radiates, radiation is basically electromagnetic radiation. It's light, it's infrared light. That infrared light actually has sufficient energy to destroy your superconductor. So this is the reason why we have to put our devices also into other kinds of shields, which are not for temperature, but to protect them from this radiation from coming and destroying the superconductivity. And if you destroy superconductivity, you get friction, and that will induce decodings.
So there's a question of a similar kind. Will the qubits get distorted or disturbed if the temperature rises a little bit? And I think your question really answers that in a very different way.
Yeah, so depends on how much temperature rise you're talking about. If 10 millikelvin becomes 15 millikelvin, in fact, routinely these systems, depending on the stability, can sometimes fluctuate in temperature. Actually, it's quite challenging to measure the temperature at such low values. So sometimes even you can get false reading because of electrical noise. But somewhere between 10, 20, 30 millikelvin, the qubits will not feel the effect so much. But after about 50 millikelvin and approaching 100 millikelvin, you'll start having these effects that the number of regular electrons will start increasing, and then other effects start to take. And this ratio of temperature to the energy gap also starts deteriorating. But small fluctuations of order of few millikelvin or even 10 millikelvin is okay for the qubits.
So there is this question from Saurav Tripathi on YouTube, and he is asking a very rudimentary question for everybody. But I think he's speaking for most of the people who do not understand too much of this technology. And his question is that, do this qubit-based architecture will eventually, he's preempting right now, but will it have the similar set of instructions that your typical 86, 386 and 486 and ARM-based architecture? Will it be something similar?
That's a nice question. In fact, there are people who are already thinking about those sort of things. Right now, the computers are very small. So one doesn't really have to worry about having a standardized format for sending instructions. Like, for example, we don't do that in our lab because we're only working with a few qubits. But one of the projects we are doing is a 7-qubit system. So there we are trying to develop some higher level. So this is basically saying that, you'll be able to write some program in some regular language, and then some compiler or operating system will take care of converting it. So people are already working on that. The instruction set will look similar in the sense that the ideas will be the same, but of course they will not be exactly the same, because the operations you do on a classical computer are different than the operations you do on a quantum computer. So the corresponding mapping has to be done correctly. But eventually, as these systems become bigger, and people already in anticipation of this have come up with protocols, there are even some open source data where people are sharing this so that everybody can use that. But ultimately, at some level, you will have to make it specialized for the particular hardware you have to use. So, there's a 2-qubit gate called the C0 gate. And we all know the C0 gate does a certain operation on a qubit, but exactly how it does will change. In a superconducting circuit, it will be composed of a bunch of microwave pulses. In an ion trap system, it will be composed of a bunch of laser pulses. So that part translation has to be done by some piece of software and hardware, which is all regular software and hardware.
So in a sense that you will still have an interface between the qubit system and the normal human machine interaction kind of thing.
Yes,
and
yes.
there, at some point of time, you will still be requiring some silicon technology to translate some of the things. So do you see any effect on or the latency in the system, overall latency?
No, the latency won't really be a problem because right now everything is sort of one way, in the sense that instructions come and then we execute and it ends. When error correction comes in, then a feedback mechanism is needed. Okay. So there, some silicon electronics and the qubit electronics will have to be integrated, and people are working on figuring out how to do this cryogenically. Right now, the way it is done is that the signal actually comes out of the fridge, gets processed, and then goes back into the system. And that can actually have a few hundred nanoseconds of delay because it takes time for light to travel, finite distances. So that will be, people are trying to develop cryogenic electronics to make that feedback faster. But eventually, this is something I often say, that eventually a full quantum computer will probably be more than 90% conventional electronics and conventional technology. There's only a core part which is quantum, and you need all this other stuff to come around it at a different sophistication level, which currently doesn't exist, and people are working on that.
So just like your funding agencies, people also would like to know one particular thing: when would be a practical computer be available based on qubits? And it's a very valid question, because finally it's the taxpayer, and the taxpayer's money comes to you.
Yes, that's a tough question, and people have been giving the same answer for the last 20 years.
Yeah, exactly.
So that's right. We thank the taxpayers. But the thing I find is that taxpayers really don't have any say. Somebody else makes the decision for them. But thank you, taxpayer, for funding this research. There are different ways or different answers to that question. In some sense, quantum computers are already here. I'm sure some of you have already logged on to the website and used the quantum computer. That itself is quite amazing, the fact that we can do that. Now, most of those computers today are not yet useful for practical applications. But this is how technology goes. But I think because we're living in the era of social media and a lot more connectivity, we have got to learn about these intermediate stages and interacting with them a lot faster than what would have happened, traditionally. Maybe you would have never heard about these things till they became really, really like proper and commercial. Part of this is also the challenge that quantum computing applications are still being developed. we haven't fully understood the scope of what all a quantum computer can do. We have these example algorithms like Shor's algorithms, Grover's algorithm, and we know quantum simulation, which is basically modeling nature, because nature is essentially understood by laws of quantum mechanics. And it turns out that it's a lot more efficient to study these quantum mechanical systems on a quantum computer, because it uses the same laws as opposed to trying to write the equations on a regular computer. So one of the big applications is there. So people are trying to see that with these 50 qubit and 100 qubit, and now I guess with IBM's 400 qubits, can we actually use them? Main problem is the error part, that all of these things are unstable. So till we solve that, real world commercial applications might still, be challenging. But I think given the progress in the last 5 years, where we have gone from maybe just a few qubits to up to 400 qubits, I think this is only going to happen very soon. I want to say maybe we will see commercial applications in the superconducting qubit technology, maybe on the scale of 5 years, but it's a little bit difficult to predict, because unless we get this error correction working, and it's proven to be quite a challenge. People have shown in principle that the idea works, but it will take time. But I think really widespread use will probably take at least a decade. But I'll add another point here. Do not expect quantum computers to show inside your home. Okay, that is really not the path this technology is going to take. At least most of us don't think that. There are some technology options where it might be possible to imagine something, the size of a phone, but that is really not needed. I like to give the example of voice recognition, like Alexa or Google Home or Siri. The machine you buy is a few thousand rupees machine. It's extremely cheap, but it doesn't do much. All it does is relays your command to a big supercomputer which is sitting somewhere in the world. And the quantum computer is going to be the same type. So even though that computer doesn't sit in your home, because of network connectivity, you're able to get the power of that massive supercomputer which is sitting somewhere, or a big cluster of machines. Similarly, quantum computers will mostly be accessible via cloud, and that's absolutely fine. And that is the model. You have to really think of quantum computers as specialized supercomputers, and they will be in data centers and other places, and you will log onto them. Unless there are special needs, for like defense and strategic purposes, where you don't want to use a public system, you will have your own hardware sitting. And you can't imagine this gigantic thing sitting in your home right now. So people often have, this is not practical, but it is practical if it is sitting in a data center, because the power it offers is unparalleled. There is no equivalent to that. There's no alternative available, and will never be available to the best of our knowledge. Classical computers just cannot get powerful enough to solve the kind of problems a quantum computer promises to do that.
So apart from such challenges, do you also face on a day-to-day basis some challenges from the material science kind of thing, that some materials are more dielectric, that this and that, and some are not suitable or something of that sort? Also, because you're talking about very, very tiny scales, nano scales. So I think the various different physical, quantum physics parameters and everything also change a lot. So do you face such things in those materials as well?
Madhavi, you want to take that?
Sure. So yeah, there are very specific materials that we choose to use because they have been studied as for the ideal properties that we want. For example, to make the Josephson junction. I mean, people are researching many different metals to do different parts of what is patterned on the chip. But the Josephson junction itself, everybody is using aluminum because it has now over the years, many people have tried different materials, but aluminum seems to be
better fit.
And the reason for that is that the Josephson junction itself, which forms the inherent nonlinear part of the qubit, that Josephson junction is basically an insulating layer sandwiched between two layers of aluminum. And the growth of the oxide of that insulating layer is best understood and best controlled in aluminum. So
it's more stable.
It's more stable as well. And the dielectrics, yes, we are trying to, so we choose, the substrate that we use is high resistivity silicon because we don't want any loss to go inside there. We don't want any kind of channel of conductivity in there. So high resistivity silicon or sapphire is what we use in
crystalline.
They are crystalline. So that's what, also, so they don't have defects in them, which is the path to losses and decoherence. So to avoid all of those things, we have to very carefully choose our materials. In superconducting circuits, a lot of this has grown historically because the materials that have worked have kind of gone forward and propagated. But in recent years, there is a fair amount of research to also explore other materials, see, have we just been blindly following this one path, and is there something out there that's better? So in parallel, that work is also going on. But for the better part of it, people are using a standard of maybe 4 or 5 metals, and the junction is almost always aluminum. The substrate is almost always silicon or sapphire.
Yeah, so we have come to the end of this session. Thank you, audience. But before we say goodbye, I would like to remind you of another technology, silicon-based technology, and that is what we will discuss in our next Chai at the Prithvi Theatre on February 5th. And that is transistor at 75. When the whole transistor became operational, when the research, basic research was, oh, will this transistor even work? And let's keep our anxieties till the 5th of February to listen from our expert, Dr. Satyanarayana, on 75 years of the transistor, the mighty transistor. Thank you very much. Goodbye. Since this is an online session, we cannot cater to your chai. So I hope you will have wonderful chai or whatever your lunch time, a Sunday lunch. Fantastic. Thank you very much. And thanks for the whole team. It was a fantastic show. Well, Madhavi. And